So in the last video, we looked at trying to find the area under this curve from 1 to 3 by approximating it using some rectangles. And the algebra here kind of got a little bit clunky. So there should be a better way to try to figure this out than writing it all out like this, and there is. So if we take maybe a little bit of a closer look at our graph here, and I'm gonna rename our x values here. So let's say that starting value here is x sub naught, or x sub 0, and then the next rectangle over, right? We've got x sub 1, x sub 2, x sub 3, x sub 4. And then we were doing the right-hand rule, and so the height of each one of our rectangles we figured out by using, the x on the right-hand side. And so the height of this first rectangle is f of x sub 1. So I'm just going to rewrite this. This here is f of x sub 1 times 1/2 plus f of x sub 2, so that's this next rectangle, times 1/2, plus f of x sub 3 times 1/2, plus f of x sub 4 times 1/2. Okay, so that's getting there. So notice everything here is kind of staying the same except we're using different x's, right? x1, x2, x3, x4. So the pattern here is we have f of some x, and we're keeping track of it with some number we're going to call I for index. And we're multiplying that by 1/2, which 1/2 was our delta x. So just for now, I'm going to put delta x back in here. So this f of x sub I times delta x, again, this is the area of a rectangle. And what we've done is we've added up all of these areas. And so we use this Greek letter sigma. Sigma, I guess, because it's an S for a sum. We're summing up all these areas. And we're going to take the sum from I equals 1. And in this case, we stopped at 4. So we're going from 1 to 4. Okay, so this is the more kind of succinct or efficient way of writing out this big long sum. Now to kind of generalize this a little bit more, we don't need to always do four rectangles. What we will see, in this video and in later videos, that we can look at n rectangles. And so we have f of x sub I times delta x. So this is the Riemann sum of our function, f of x, using n rectangles. Now, there's just some things we should know about this summation notation that's going to come in handy. First off, the part that's changing here is the I, right? So we're going from x sub 1 plus x sub 2 plus f of x sub 3 plus f of x sub 4. So we can kind of think of that I as really being our variable in a sense of the sum. So let's look at a different sum real quick. We've got the sum from 1 to n. How about of just I? So what is this sum? This sum is 1 plus 2 plus 3. I'm starting at 1 and I'm going all the way to n. Okay, so this sum, 1 plus 2 plus 3 plus 4 plus 5, all the way up to n, this has a nice formula that's going to come in handy a little bit later. So this formula is n times n plus 1 over 2. And this is true for any number n. If I start at 1 and I add up all the way to n, if I do n plus the very next, or times the very next number, divide that answer by 2, I get the answer for this sum. There's another one that comes in handy. And this is I squared. And so this is the same thing, right, as 1 squared plus 2 squared plus 3 squared plus ... n squared. This has another nice little formula. It's n times n plus 1 times 2n plus 1 over 6. I'm not going to offer any kind of proof for these right now. We're just going to kind of take these for granted, and we'll end up using them in some later videos. A couple of other ones that are handy. So let's say that C is some constant. So what this formula is C plus C plus C plus ... plus C. And we've done that n times. And so an easier way of doing this, like adding with style, right, is multiplication. So we have C times n. So that one's going to be handy. And then a couple that we kind of end up taking for granted, but are nice to kind of see written out too, is, well, let's see. How about if I have C times I? So this one, you can think of this as like C times 1 plus C times 2 plus C times 3 all the way, oops, I didn't finish my notation, times plus C times n. So here, I've got the same thing as like the sum of I, right? Except I've got these C's in here. So we can just factor out that C, and then we're left with a sum that we're familiar with. And so this is just C times our sum. Okay, now it kind of didn't matter that we had the sum of I here. We could have had any sort of thing here times our constant. What this shows us, though, is that we can just factor out our constant, that it just factors right out of our sum. We can, in a sense, kind of pull it out of the sum. So there's that one. Another one, I'm just going to use an example to kind of motivate it here. Let's say we had 1 plus 2 plus 3 plus 4 plus 5 plus 6. Now, test it out, but I'm going to say that this is the same thing as 1 plus 3 plus 5 plus 2 plus 4 plus 6. Don't take my word for it. Test it out. Make sure that I'm not lying to you. But if this is true, we can use this in a new rule here. So the sum of, let's say, A sub I plus B sub I. Let's say that like A sub I is like all the odd numbers, and B sub I is like all the even numbers. So what we've shown you up here, right, is if I'm adding up odd number plus an even number plus an odd number plus an even number plus an odd number plus an even number, it's the same thing as if I just add up all of the odd numbers and add to that the sum of all the even numbers. So I can split up these inner sums. I can split up these inner sums into, I guess, outer sums. So this all ends up coming in handy when we do some kind of bigger problems, which we'll see in the next video. This one's getting kind of long. So just kind of hold on to, all of these kind of ideas, these ones that we saw here, and then this one we just saw here. These will all come in handy very soon.